Hi. Today looking at the pattern as an 8 going to question 12. So question 12 gives us a geometric figure and tells us if AD is AC, AB is BC is CE. Right? All these sides here are the same length. Find the ratio of the area ADCE, so this shaded region, to the area of ABC, this shaded region. Okay, so the way to start this question is by labelling what we know. So we know that we have an equilateral triangle. So we don't have an angle of 60 degrees, and we can arbitrarily label the side length to be x. Well, that tells us that we have a side length of x here and a side length of x here from the question, and then we know these two are x because it's an equilateral triangle. Okay, well now we can find the area of our circle, of our triangle ABC. We know the formula for the area of a triangle is half AB sine C, A and B being adjacent sides and C being the angle between them. So plugging that in, we get the area of ABC is half AB, so half x times x squared, times sine of C. C is 60 degrees, sine of 60 degrees is root 3 over 2. So that gives us root 3 x squared over 4. X squared over 4. Okay, well now what do we need to know? Well, we need to find the area of this large circular sector. And in fact, we need to find the area of this circular sector here and then subtract the area of this smaller circular sector. I'm just going to label on here. You see there's actually a smaller circular sector there. So we need to find the area of that. So we can subtract this from the area of the large one to get the area of the shaded region ADCE. Well, let's just remove that to make it more useful, more clear. So what we can do, let's find the radius of our large circle. If we find the radius of our circle, then we can find the area of it. So what is our radius? Well, we know the distance from here to here is the same as distance from here to here. So if we call that R1 because it corresponds, you notice, to the area of our smaller circle, then we know that we have a 90-degree angle here. This bisects the angle, so it's 30 degrees, and then we have a side length of x over 2. So that tells us we know cosine is adjacent over hypotenuse. The adjacent is x over 2, and the hypotenuse is r1. Cosine of 30 degrees is root 3 over 2. Well, therefore, r1 is equal to x over 2 times 2 over root 3. And that comes out to x over root 3. So if we call A1 the area of our small circle, so we'll call A1 small and A2 large, well, we get that A1 is now equal to pi times its radius squared. Its radius is x over root 3, so x squared over 3. So that's the area of our circle, our small circle here. If we imagine we extended it round like this. Okay, now what about the area of our large circle? Well, A2, this is in blue, is equal to, well, pi times the radius squared. And what's the radius? Well, clearly the radius is x plus this distance here. And this distance here, we just said is R1, because it's going to be a same distance from any vertex to the origin. So it's R1 plus x. So that's equal to R1 x over root 3 plus x all squared. Well, that's equal to pi x squared into 1 plus 1 over root 3 all squared. And that's equal to pi x squared into 1 plus 2 over root 3 plus 1 over 3, which comes out to 2 pi x squared into 2 plus root 3 over 3 when we simplify it. So what we'd do there is we simply add the 1 and the third to give us 4/3, bring out the 2, and then multiply top and bottom by root 3 to rationalise it. Okay, well now how do we find this shaded region? Well, what we notice is this shaded region is actually a sector of this large circle minus the sector of this small circle. So if you take this large sector area and subtract this small sector area, you get the area of the shaded region. If you can't see that, let's visualize it this way. So we have this sector region, if we find that, and then we subtract this section here, Well, that's in fact the sector area of the solar circle. Then we get left with just the shaded region, which is what we're concerned with. Well, we need to find the angle here to do that. What is this angle? Well, we know this is going to be 30 degrees, and we know this is going to be 30 degrees because they're bisecting the angle. So this means this is in fact 120 degrees. Or that this side here is 240 degrees. So we know that what we do is we do 240 degrees over 360 degrees times the area of the circle. So that means our area ADCE is equal to 240 over 360 times the area of our large circle, which is 2 pi x squared into 2 plus root 3 over 3 minus 240 over 360 times the area of our small circle, pi x squared over 3. Well, 240 over 360 is 2/3. So this gives us 4 pi x squared over 9 times 2 plus root 3 minus 2 pi x squared over 9. Okay, well that's equal to 8 pi x squared plus 4 root 3 pi x squared minus 2 pi x squared over 9, which comes out as 6 pi x squared plus 4 root 3 pi x squared over 9. Okay, so we're asked to find the ratio of the areas. So that's simply going to be area of ADEC over the area of ABC. Well, that's 6 pi x squared plus 4 root 3 pi x squared over 9 divided by the area of ABC, and that was equal to root 3 over 4 x squared. Okay, so doing that, we get 6 plus 4 root 3, and we'll factor out the pi x squared over 9, and then we take the reciprocals, that's times 4 over root 3 x squared. So we see our x squared cancel, and this is equal to 6 plus 4 root 3 pi times 4 over 9 root 3. Well, we can take out a 2 from this bracket here, so that's equal to 8 pi into 3 plus 2 root 3 over 9 root 3, or if we multiply top and bottom by root 3, we get 8 pi into 3 root 3 plus 2 root 3 times root 3 is 2 times 3 is 6 over 9 times 3 27. And we know there's a factor of 3 cancels to give us nicely that the ratio of the areas is root 3 plus 2 over 9 times 8 pi.